Hello viewers, I am Dr. Devesh Gupta, Senior Professor and Head, Department of Radiological Physics, Dr. SN Medical College, Jodhpur. Today I am going to talk on interaction of particle radiation with matter. To calculate the dose to the patient, how particle interact with the body, knowledge of this we required. For more and more knowledge about interaction of particle with body, we can we can use various type of particle radiations in the cancer treatment. Nowadays, electrons are very frequently used particles for the cancer treatment, for especially superficial tumors. Protons, neutrons, helium particles are also used, or I can say introduced in the cancer treatment. So in the coming slides, in this we will see how these particles interact, how these particles are measured, dose measured, detected, and the knowledge of this is used in the cancer treatment. The objective of our present topic is type of interactions, the Bragg curve, energy straggling, range of charged particle, range straggling, range of beta particle, linear energy transfer, Cerenkov radiations, and at the end, summary of all these. Introduction. Radiation therapy is based on the exposure of malign tumor cells to significant but well localized doses of radiation to destroy the tumor cells. The goal is to maximize the dose to the tumor location while minimize the exposure of the surrounding body tissues. Radiation therapy can be performed by using external radiation sources, that is charged particle exposure by accelerator beam, neutron exposure by reactor beam. This is a part of external beam therapy, or by using internal radiation sources, either low dose rate machine or low dose rate, medium dose rate or high dose rate radiation sources in close vicinity of the tumor, that is a brachytherapy. All have no net charge. They are electrostatically neutral. In order to detect them, they must interact with the matter and produced an energetic charged particle. In the case of gamma and X-rays, a photoelectron is produced. In the case of neutrons, interaction with any matter, a proton gets kinetic energy in collision. In case of neutron, when it interacts with the medium, since the proton mass is equivalent or almost equal to neutron, maximum energy is transferred to proton, and proton gets energy and will move in the medium. And since it is a charged particle, it ionizes further the medium. Light charged particles like electrons, excitation and ionization of atom in absorber medium, that is atomic effects, interaction with electrons in material, that is collision and scattering, deacceleration by Coulomb interaction, that is Bremsstrahlung production, heavy charged particle, Z is more than 1. In that case, excitation and ionization of atoms in absorber medium, that is atomic effects takes place. Coulombian interaction with nuclei in material, that is collision and scattering, long-range forces. Neutron radiations, interaction by collision with nuclei in material, that is short-range forces. Energy loss and dose are correlated with each other and help to formulate the interaction of internal and external radiation with matter in to predict the effectivity of the radiation treatment and the possible change in adjacent body tissues. Figure shows how the photons interact with the material. Radiation treatment is based on different kind of radiation and depends on the different kind of interaction between the radiation and the matter, that is body tissues. The interaction between radiation particles and the absorber material determines the energy loss of the particles and therefore the range of the particle in the absorber material. We are talking about charged particle or radiation particle, where how it interacts with the medium, the amount of energy absorbed in the body depends on its interaction. Each interaction process leads to a certain amount of energy loss. Since a fraction of the kinetic energy of the incoming particle is transferred to the body material by scattering, excitation, ionization, or radiation loss. The sum over all energy loss events along the trajectory of the particle yields the total energy loss. Now, various type of interactions. Basically, there are two type of interactions. One is collision interaction. This is an inelastic collision with atomic electrons. This results in excitation or ionization. These processes ultimately end with the heating of the absorber through atomic and molecular vibrations, unless the ions and electrons can be separated using an electric field, as is done in radiation detectors. In this, when a charged particle interacts with the atom, excitation of the atom takes place, and due to the vibration, energy is generated. Second type of interaction is radiative interaction. This is an inelastic collision with nucleus. A quantum of electromagnetic radiation is emitted, that is, photon is coming out. There is an energy loss of the incident particle, especially for electrons. Probability of nuclear excitation is negligible. Basically, particle interacts with the Coulombian field of the nucleus. This process is also known as radiative energy loss. The detection of electron due to Coulombian, this is the process by which X-rays are generated. When high energy electrons interact with the target and X-rays are generated, this is a radioactive interactions. Now this figure shows the two type of interactions. One is collisional interaction and second is radiative. Now, how the stopping power, this is showing that two different stopping powers. Energy loss by ionization, which dominates for lower energies and low jet material. Absorbed dose delivered to material via this process. Second is radiative stopping power, scattering mainly by nuclei due to Coulombian field, energy loss by photon emission, that is Bremsstrahlung production, dominates for high energy electrons and high jet target material. What is stopping power? The stopping of charged particle in matter is by collision and radiative processes, which occurs in frequencies dictated by their interaction cross-section or the probabilities. What we observe then is a statistical average of two processes occurring as the particles slow down. Linear stopping power is given by this mathematical expression S is equal to minus dE by dx, where E is the charged particle kinetic energy, minus dE is the energy increment lost in infinitesimal material thickness of dx. The units of stopping power are kilo electron volt per micron. The higher the stopping power, the shorter the range into the material the particle can penetrate. The quantity S is also referred to as a specific energy loss. The stopping power S increases as the particle velocity is decreased. The classical depiction of the charged particle interaction with an electron is depicted as below. As the velocity of the particle increases, energy transfer to electron will be less. Classically, charged particle passing close to electron will impart kinetic energy to the electron given by the following formula. This mathematical formula is given. The classical, that is non-quantum mechanical expression that describes the specific energy loss is known as the Bethe-Bloch formula. This is a classical interpretation of the dose or the range of the particle in the medium. Electrons are light mass particles, therefore scattered easily in all directions due to their interaction with the atomic electrons of the absorber medium. This results into more energy loss per scattering events. But this is not the case in the heavy charged particles. Now, because of the scattering, the energy straggling takes place. Energy loss in a material is a statistical or stochastic process. Therefore, a spread of energies always results when an initially monoenergetic beam of particles encounters an absorber. Many particles lose the average energy, although some will lose not so much and some will lose more than the average. This results in a finite width to the energy distribution curve known as energy straggling. The straggling peak is approximately Gaussian shaped with a width that increases with the ratio Z by A. At lower atomic numbers, where the Z by A ratio is higher, we have wider widths. This is due to the fact that there is less shielding of inner electrons in the lower Z elements, and hence there is more stopping influence per electron. Mass stopping power. It is also known as mass attenuation coefficient, which is defined as mu by rho, where mu is the linear attenuation coefficient and rho is the absorber density. The mass stopping power is given by the equation 1 by rho dE by dx, and its unit is keV per gram per centimeter square. Bremsstrahlung and stopping power. The total stopping power for electrons can be given by a combination of the collision and radiative type of interactions. The multiple scattering results in a very limited spatial resolution of the electron beam within the absorber material. The energy loss of the electrons is dominated by excitation and ionization effects, dE by dx of excitation, and by Bremsstrahlung loss dE by dx at radiative loss. So, The total stopping power dE by dx total is sum of dE by dx excitation plus dE by dx radiative. The energy loss component depend sensitively on the charge number Z and the average ionization potential I is equal to 11.5 into Z electron volt of the absorber material. The number density n, the relativistic velocity of the electrons small v with mass m0. The dE by dx excitation is given by this expression. The second term is proportional to Z square and energy E, which is dE by dx of radiative is given by the expression. The ratio between these two components, first is the energy loss due to excitation, second energy loss due to radiative process. The ratio between these two components depends on the energy of the electron beam E and the charge Z of the absorber material. On the basis of the approximation for the percentage of the energy loss to radiation for monoenergetic electrons, dE by dx of radiative divided by dE by dx total is equal to ZE by upon 1000. For heavy ions, the electron loss is described by the Bethe formula in terms of the number density n and charge number Z of the absorber material and the charge number Z, mass m0 and velocity v of the projectile, dE by dx is given by this expression. The average ionization potential is I is equal to 11.5 Z electron volt. The energy loss is used to calculate the stopping power for the projectile in the material and their range. The stopping power is defined as the energy loss per distance, S is equal to minus dE by dx, or as energy loss per distance and number density, or the density is given by this expression. There is one example for lead with Z value is 82 and E is more than 8.5 MeV, radiative losses dominates. When energy of the particle is more than 8.5 MeV or equivalent to this, radiative losses dominate, and the graph shows for that. The another point to understand is how a charged particle loses its energy with depth. This shows by the Bragg curve. The heavy particles, the plot of a specific energy loss which can be related to a specific ionization along the track of a charged particle is called a Bragg curve, which is also shown in the slide. A typical Bragg curve is depicted in the following graphic for an alpha particle of several MeV of initial energy. As the energy falls, the specific energy loss increases according to the Bethe-Bloch formula. As the energy falls below a threshold, however, an electron will attach to the alpha dramatically lowering the specific energy loss. The Bragg curve for electron. The energy deposition of the electron increases more slowly with the penetration depth due to the fact that its direction is changed so much more drastically. In fact, there is no increase in energy deposited near the end of the track, and the Bragg peak for electron is never observed. It seems that for electrons and their tortuous path, the energy deposition is spread in the transverse direction as it progresses forward in the initial direction until the last 1 keV, which is deposited pretty much along a straight line in the forward direction. Range of charged particles. The range of charged particle can be derived from the stopping power formula mathematically shown. Heavy particles are less scattered than electrons due to their heavy masses, and the beam shows significantly better spatial resolution. Because of the strong interaction with the absorber material, electrons experience immediate energy loss and the intensity drops rapidly. This limits the range of the electron beam in the material, and the range is given by the expression. The stopping power is proportional to Z square. It increases rapidly at low energies, reaches a maximum and decreases gradually with increasing energy. This can be seen in the graphs. Because of the specific energy dependence of the energy loss or stopping power curve, incoming high energy particles experience only little energy loss, dE by dx, but the energy loss maximizes when the particles have slowed down to energies which corresponds with the peak of the energy loss curve. The energy of the particles with an initial energy EI at a certain depth d can be derived by the expression. The position d max of maximum energy loss can be directly calculated from the initial energy and the stopping power of the projectile in the absorber material, and which is given by the expression d max is equal to integral 0 EI minus ED and so on. For protons, the energy loss maximizes at energies around ED is equal to 100 keV. For alpha particles, it is around 1 MeV. In the diagram shown in the slide, a source of monoenergetic alpha particles is directed at a particle detector through an absorber. We know the initial monoenergetic spectrum will demonstrate energy straggling, but the direction of the particle should not be altered and they should all make it to the detector, provided the thickness of the absorber is less than the thickness required to stop the slowest of the distribution. This is shown as the constant horizontal line in the graph at the bottom of the drawing. Once the absorber thickness is such that some of the slower particles are stopped, the width of the energy straggling curve presents itself in the slope of the fall-off from constant particle number detected down to 0. Now in this graph we see that there is a sharp fall and then there is a very small penumbra in the graph. The mean energy in the range at which the number of particles detected is 1/2 the original value. The same experiment can be performed with a beam of electrons or beta emitter. In this case, however, the electrons are more vulnerable to wide angle scattering even in the thinnest of foils. So wide an angle that the scattering electrons will not be detected. The result is an immediate fall off in the number of electrons detected as a function of absorber thickness, as demonstrated in the drawing. Here we can see in the graph that there is a bigger penumbra which is a result of Bremsstrahlung. Factors which affects range are energy. Range is approximately linear with energy. Since the Bethe-Bloch equation for stopping power is inversely proportional to energy. This we can see from the mathematical expression of the classical Bethe-Bloch formula. Second parameter which affects range is mass. For the same kinetic energy, the electrons is much faster than the alpha due to its smaller mass, and therefore the electron has less time to spread near orbital, less time to spend near orbital electrons. This reduces the effect of Coulombian interactions, hence stopping power, and increases the range. Third parameter which affects the range is charge. The more charge, the more stopping power and the lower range. Range is inversely proportional to the square of the charge particle. For example, a tritium particle with Z is equal to 1 will have 1 by 4 the stopping power of helium with 3 particles with Z is equal to 2. The another parameters which affects the range is density. The stopping power increases with increasing density. The range is inversely proportional to the density of the shielding material or the shielding medium. Range straggling. The same factor which are responsible for energy straggling also plays significant role in straggling of range. The total path of energy depletion is different for each initial mono-energetic alphas. Differentiating the cutoff curve often is used to demonstrate a range straggling curve similar to the energy straggling curve. Scaling laws. Experimentally, it is not possible to find range of all possible incident particles for all possible absorbing material at all possible energies. In order to estimate the range or energy loss characteristics of a particle, basic assumptions such as validity of the Bethe-Bloch formula and the stopping power per atom of compounds or mixture of is additive are considered. The later assumption is known as the Bragg-Kleeman rule. The Bragg-Kleeman rule calculates the range of particles in a material for which no information regarding energy loss or range of the particle is known, but has been given range information in another material. The approximation becomes less valid as the separation in atomic weight increases. This rule is mathematically given here in this slide. Positron. Positrons behave in the same way as electrons. When positron loses their energy, they are simply deflected in the opposite direction. As far as imaging is concerned, the 511 keV annihilation photons resulting from positron comes from the point at which the positron has showed enough to energy in a prolonged encounter with an electron. That is, it forms the unstable positronium. This places an isotope dependent limit on spatial resolution in PET imaging. Since each positron emitter has a different E max for positron and hence a different range. The other consideration is the center of mass momentum of positronium, which contributes to non-opposition of the annihilation photons in the laboratory frame of reference. Cerenkov effects. When a charged particle is emitted in the radiative decay with velocity greater than c by n, the speed of light in the medium, where n is the index of refraction of the medium, a shock wave of photon is generated in the blue light range, analogous to the sonic boom of a jet flying faster than the speed of sound. This is applicable in nuclear medicine in the assaying of P32, which in a water solution has a detectable by liquid scintillator apparatus Cerenkov emission. Gamma rays, X-rays, neutrons and neutrinos all have no net charge. They are electrostatically neutral. The charged particle interacts with matter primarily through the Coulomb force. The energy deposition by the charged particle in the medium depends upon its mass and charge on it. Heavy particles deposit more energy in the medium as compared to light particle. Basically, there are two types of interactions, collision and radiative. Collision interaction is an inelastic collision with the atomic electron, and radiative interaction is an inelastic collision with nucleus. The electron loses its energy by photon emission when interact with the nucleus. Due to these processes of interaction, charged particles travel a finite distance in the medium before it stops. The range of charged particle depends upon the energy, mass and charge of the particle and density of the absorber or the medium. Range is approximately linear with energy since the Bethe-Bloch equation for stopping power is inversely proportional to E. Lighter particle moves faster and far distance as compared to heavy particle. Also, range is inversely proportional to the square of the charge particle. The range and stopping power is demonstrated by a Bragg curve. The Bragg-Kleeman rule calculates the range of particles in a material for which no information regarding energy loss or range of the particle is known, but range information in another material is given. Thank you.